Welcome to a journey through the deepest mysteries of our cosmos. Let your mind drift as we explore the profound questions that lie at the very heart of existence itself. Tonight, we begin at the beginning, with the birth of reality. In the beginning, there was something we still cannot fully comprehend. The Big Bang, that singular moment when everything began, remains shrouded in profound mystery. We know that approximately 13.8 billion years ago, the universe erupted into existence from a point of infinite density and temperature. But what happened in those first fleeting fractions of a second? The earliest moments, the first trillionth of a second, are hidden behind a veil we have yet to pierce. The laws of physics as we understand them break down in those extreme conditions. Time itself may have had no meaning. Space may not have existed as we know it. We have equations that bring us close, theories that dance around the edges of that primordial instant, but the ultimate truth of how something emerged from nothing, or from whatever came before, remains one of the deepest puzzles in all of cosmology. What force drove that initial expansion? What determined the fundamental constants that would shape everything to follow? These questions linger in the quiet spaces between our knowledge, waiting for answers that may reshape our entire understanding of existence. As we contemplate that ancient beginning, we encounter another bewildering concept that extends far beyond our visible cosmos. Eternal inflation suggests that our universe might be just one bubble in an endlessly frothing cosmic sea. According to this theory, the inflationary period that caused our universe to expand rapidly in its first moments never truly ended everywhere. Instead, it continues in vast regions beyond our observable horizon, constantly spawning new bubble universes, each with potentially different physical laws and constants. Imagine an infinite expanse where universes bloom like bubbles in champagne, each one a separate cosmos with its own history, its own stars, its own possibilities. Our entire observable universe, with all its billions of galaxies, would be merely one tiny bubble in this eternal multiverse. Time loses its conventional meaning in this picture. There is no universal clock, no synchronized moment of beginning. Some bubbles might be ancient beyond our comprehension, while others are just now coming into being. We may never be able to observe these other bubble universes directly, separated as they are by regions of space expanding faster than light can travel. Yet the mathematics of inflation theory almost inevitably leads to this conclusion, leaving us to wonder whether we inhabit just one room in an infinite cosmic mansion. Perhaps our universe's beginning was not truly a beginning at all. The Big Bounce hypothesis suggests that what we call the Big Bang might have been a transition, a cosmic rebound from a previous universe that had collapsed. Instead of time and space emerging from nothing, they might have passed through a bottleneck, compressed to an unimaginable density before expanding outward once more. This cyclical model proposes that the universe undergoes endless cycles of expansion and contraction, bouncing eternally through phases of creation and dissolution. Each bounce might preserve some information from the previous cycle, or it might wipe the slate entirely clean, leaving no trace of what came before. The mathematics of quantum gravity, still being developed, might allow for such a bounce, preventing the singularity that classical physics predicts. If this is true, then our universe has no ultimate beginning and will have no final end, just an eternal rhythm of expansion and contraction, playing out across timescales that dwarf our current cosmic age as much as that age dwarfs a human lifetime. We are left to wonder whether we live in the first bounce, the millionth, or an iteration in an infinite sequence, with no way to know what came before or what imprint it might have left on the universe we inhabit. The shape of the universe itself presents another profound puzzle. We tend to imagine space as flat and infinite, extending in all directions without boundary. But the universe's topology, its global geometric structure, might be far stranger. Space could wrap around on itself in ways that challenge our intuition. Like the surface of a sphere, the universe might be finite yet have no edge, so that traveling far enough in one direction would eventually bring you back to your starting point. Or space might be connected in more exotic ways, forming shapes like a torus, where the universe folds back on itself in multiple dimensions. There could be shortcuts through space, wormhole-like connections that link distant regions. Current observations suggest the universe is very close to flat on the scales we can measure, but this doesn't rule out subtle curvature or topological features that manifest only on scales larger than our observable horizon. We might live in a universe shaped like a dodecahedron, a horn, or some higher dimensional form we can barely visualize. The cosmic microwave background, that ancient light from the early universe, might contain subtle patterns that hint at these topological features, like an echo bouncing back to us through a curved space. But detecting such patterns requires extraordinary precision, and so the true shape of our cosmic home remains hidden, perhaps forever beyond our ability to fully map. Speaking of that ancient light, the cosmic microwave background itself whispers secrets from the universe's infancy. This radiation, released when the universe was just 380,000 years old, fills all of space with a faint glow, now cooled to just a few degrees above absolute zero. When we map this radiation across the sky, we find it remarkably uniform, the same temperature in every direction to within 1 part in 100,000. But within that uniformity lie tiny ripples, minute variations in temperature that represent the seeds of all cosmic structure. These ripples show us where matter was slightly more or less dense in the early universe. Gravity would amplify these tiny differences over billions of years, pulling matter into the galaxies, clusters, and cosmic web we see today. Yet the exact pattern of these ripples contains information we're still learning to decode. The size and distribution of these temperature variations tells us about the composition of the universe, the geometry of space, and the physics of the first moments after the Big Bang. Each new measurement of these ripples brings us closer to understanding our cosmic origins, but also reveals new puzzles, new fine details that don't quite match our expectations. The microwave background is like a cosmic time capsule, a message from the distant past encoded in subtle patterns of light, still being translated by each generation of astronomers. Among these patterns, one particularly unsettling feature has earned an ominous name: the axis of evil. This refers to an unexpected alignment in the cosmic microwave background's largest scale temperature variations. According to our best theories, these patterns should be randomly oriented, with no preferred direction in space. The universe should have no special axis, no cosmic direction that stands out. Yet observations have revealed that several of the largest features in the microwave background appear to be aligned with each other and with the plane of our solar system in ways that seem statistically unlikely. This alignment has been confirmed by multiple satellites and appears to be real, not an artifact of our instruments. But it shouldn't exist. It violates the cosmological principle, the idea that the universe looks the same in all directions on large scales. Some physicists have suggested it might be a statistical fluke, an unfortunate coincidence that looks meaningful but isn't. Others wonder if it points to some fundamental asymmetry in the universe, perhaps a remnant of the inflation epoch or evidence that our universe is rotating or has some preferred direction. The alignment with our solar system is particularly troubling, seeming to place us back at some kind of center reminiscent of pre-Copernican thinking. Most scientists suspect there's a mundane explanation we haven't yet found, perhaps some subtle systematic error in how we analyze the data. But until we understand it fully, the axis of evil remains an uncomfortable thorn in cosmology's side, a reminder that the universe might still have surprises that challenge our fundamental assumptions. As we probe deeper into the cosmos's expansion, we've encountered another troubling puzzle known as the Hubble tension. The universe is expanding, carrying galaxies away from each other, and the rate of this expansion is called the Hubble constant. For decades, astronomers have worked to measure this value with ever greater precision. But a strange problem has emerged. When we measure the expansion rate using nearby objects like certain types of supernovae and variable stars, we get one value. When we calculate it using the cosmic microwave background and our understanding of the early universe, we get a different value. The discrepancy is small, about 9%, but it's persistent and has grown more significant as measurements have improved. Both methods seem solid, based on well-understood physics and careful observations. Yet they disagree in ways that can't be easily dismissed as measurement error. This tension suggests that something might be wrong with our model of cosmic evolution. Perhaps dark energy behaves differently than we think, or maybe there's an unknown component to the universe that affects its expansion in unexpected ways. The universe might be younger or older than we calculate, or its expansion history more complicated than our models assume. Some physicists wonder if this is our first glimpse of new physics, a crack in the standard model of cosmology that will eventually lead to a deeper understanding. For now, the Hubble tension reminds us that even our most successful theories might be incomplete, that the universe guards its secrets carefully and reveals them only to those who look with sufficient care. Underlying all these mysteries is perhaps the most profound problem in theoretical physics, the cosmological constant problem. When quantum field theory calculates how much energy should exist in empty space itself, in the vacuum, the answer is staggeringly large, about 120 orders of magnitude larger than what we actually observe. This is not a small error, not a factor of 2 or 10. It's the worst prediction in the history of science, a mismatch so enormous it strains comprehension. Yet the universe doesn't care about our calculations. The vacuum energy, also called the cosmological constant, is real and measurable through its effects on cosmic expansion. It's just incredibly, impossibly smaller than quantum theory says it should be. Something in nature must be cancelling out almost all of this vacuum energy, leaving behind only a tiny residue. But what? And why is that residue exactly the right size to become important just now in cosmic history? If it were much larger, the universe would have expanded so rapidly that no structures could form. If it were much smaller or negative, the universe might have collapsed long ago. The fact that we exist means the cosmological constant must be in a very narrow range, yet we have no explanation for why this is so. Some physicists invoke the anthropic principle, arguing that in a multiverse with many different values, we naturally find ourselves where the constant allows for life. Others seek a deeper mechanism, some unknown symmetry or principle that forces the constant to its observed value. Until we solve this problem, our understanding of quantum mechanics, gravity, and the vacuum itself remains fundamentally incomplete. This tiny but non-zero vacuum energy manifests as dark energy, a mysterious component that makes up about 68% of the universe. Dark energy exerts a subtle but relentless push, a negative pressure that causes the expansion of space itself to accelerate. In the universe's early history, matter and radiation dominated, and gravity worked to slow the expansion, pulling everything back together. But as the universe grew larger and matter became more dilute, dark energy's influence grew proportionally stronger. About 5 billion years ago, dark energy became dominant, and the universe's expansion began to accelerate rather than slow down. Galaxies began rushing away from each other ever faster, and this acceleration continues today, gradually but inexorably. The nature of dark energy remains one of cosmology's central mysteries. Is it truly constant throughout space and time, or does it evolve? Is it a property of space itself, the cosmological constant Einstein introduced and then abandoned? Or is it something more dynamic, a field that permeates the universe and can change? We've given it a name, dark energy, but that name is really just a placeholder for our ignorance. We see its effects but don't understand its cause. As we look to the future, dark energy's dominance will only grow stronger. Eventually, perhaps hundreds of billions of years from now, it will drive galaxies so far apart that future observers would see a lonely, empty universe, with all other galaxies racing away beyond the cosmic horizon. But for now, it works silently in the background, gently pushing the cosmos toward an ever colder, ever more dispersed fate. Finally, we return to perhaps the most famous cosmic mystery of all, dark matter. Everything we can see in the universe, all the stars and galaxies and glowing gas, makes up only about 5% of the total cosmic content. Another 27% is dark matter, invisible substance that we detect only through its gravitational effects. Dark matter doesn't emit, absorb, or reflect light. It passes through ordinary matter almost without interaction, like a ghost moving through walls. Yet its gravitational pull is unmistakable. Galaxies rotate too fast to be held together by visible matter alone. Dark matter's gravity provides the additional binding. Galaxy clusters contain far more mass than we can account for with stars and gas. Dark matter fills the gaps. The universe's structure, the vast cosmic web of filaments and voids, formed under dark matter's gravitational influence, with ordinary matter falling into the gravitational wells that dark matter created. We've searched for dark matter particles in deep underground laboratories, trying to catch the rare interaction between dark matter and ordinary atoms. We've looked for signs of dark matter particles annihilating each other in space, hoping to see the radiation produced. So far, direct detection has eluded us. We know dark matter is cold, meaning its particles move slowly compared to the speed of light. We know it must be stable, lasting billions of years without decaying. Beyond that, its identity remains uncertain. Is it a new kind of particle predicted by supersymmetry? Is it an axion, a lightweight particle that emerges from certain theories? Or is it something stranger still, perhaps connected to extra dimensions or modifications to gravity itself? Until we identify dark matter definitively, our understanding of the universe remains incomplete, like trying to understand a symphony while hearing only a fraction of the instruments. The cosmos is held together by an invisible scaffolding we have yet to fully perceive, a reminder that reality extends far beyond what our eyes can see. When astronomers first measured how fast stars orbit within galaxies, they expected to find a simple pattern. Stars closer to the galactic center, where most of the visible matter concentrates, should move faster. while those farther out should move more slowly, just as planets farther from the Sun orbit more leisurely than those nearby. But observations revealed something entirely unexpected. Stars in the outer regions of galaxies move just as fast as those closer in, sometimes even faster. Their orbital speeds remain roughly constant no matter how far from the center they lie. This shouldn't be possible with the amount of visible matter we can account for. The stars are moving so fast they should fly apart, escaping the galaxy's gravity entirely. Yet galaxies remain intact, their stars held in stable orbits by some invisible presence. These galaxy rotation curves, as they're called, provided some of the earliest and most compelling evidence for dark matter. The mathematics is inescapable. There must be far more mass in galaxies than we can see, distributed in a vast halo that extends well beyond the visible disk. This dark matter halo provides the additional gravity needed to keep those outer stars bound to the galaxy. Different galaxies show different rotation curve shapes, hinting at variations in how their dark matter is distributed. Some galaxies have rotation curves that rise steeply, others more gradually, each one a fingerprint of its dark matter content. Yet despite decades of study, the precise nature of this invisible matter remains elusive. We map its effects with ever greater precision, tracing the contours of the unseen, but the substance itself continues to hide from our instruments, leaving us to wonder what comprises the majority of every galaxy's mass. Beyond individual galaxies lies an even grander structure, a cosmic architecture of unimaginable scale. The universe is not uniformly filled with galaxies, but instead resembles a vast sponge, with galaxies clustered along filaments and sheets surrounding enormous empty regions called cosmic voids. These voids are not merely sparse regions but truly empty spaces, hundreds of millions of light-years across, containing almost no galaxies at all. They are the largest structures in the universe, cosmic bubbles in the froth of existence. The walls between voids contain most of the universe's galaxies, compressed into relatively thin sheets and filaments by gravity's patient work over billions of years. How did this structure form? In the early universe, matter was distributed almost uniformly, with only tiny variations in density. But gravity amplifies differences. Slightly denser regions attracted more matter, growing denser still, while less dense regions had their matter pulled away, becoming even emptier. Over cosmic time, this process created the web-like structure we see today. The voids expanded as matter drained from them, leaving behind vast emptinesses that grew larger as the universe aged. These structures tell us about the initial conditions of the universe, about how dark matter behaves, and about the nature of cosmic evolution. The pattern of voids and filaments emerged from quantum fluctuations in the first moments after the Big Bang, tiny ripples that grew over 13 billion years into structures spanning significant fractions of the observable universe. We are still learning to read this cosmic architecture, to understand what the distribution of matter and emptiness reveals about the fundamental laws that govern existence itself. Within these cosmic voids, there exists an even subtler phenomenon revealed only through the most sophisticated observations. The Sunyaev-Zeldovich effect occurs when light from the cosmic microwave background passes through hot gas, getting slightly boosted in energy by interactions with fast-moving electrons. Astronomers use this effect to map hot gas in galaxy clusters, but recently they've detected unexpected signals from cosmic voids themselves. These Sunyaev-Zeldovich voids show temperatures and densities that don't quite match predictions. The void should be almost entirely empty and cold, yet some show signs of containing more gas than expected, gas that might be warmer than it should be. This could mean that our understanding of how matter distributes itself on cosmic scales is incomplete. Perhaps there are filaments of warm gas threading through the voids, remnants of ancient galactic winds, or material that never fully condensed into galaxies. Or maybe the voids aren't quite as empty as we thought, containing diffuse matter that we failed to account for properly. The signals are subtle and difficult to interpret, requiring careful analysis to separate genuine cosmic phenomena from instrumental artifacts or foreground contamination. Each new survey reveals more detail, more hints that the voids might harbor secrets we haven't anticipated. Understanding these Sunyaev-Zeldovich anomalies matters because voids make up most of the universe's volume. If we misunderstand what happens in these empty spaces, we misunderstand the universe as a whole. The voids might seem like featureless regions, uninteresting compared to the busy galaxy clusters and bright stars, but they too have stories to tell about cosmic evolution and the hidden contents of space. Turning our attention to the beautiful spiral galaxies that dot the cosmos, we encounter another persistent mystery in the elegant curves of their arms. Spiral arms appear to be relatively stable features, maintaining their shape over millions or even hundreds of millions of years. Yet the stars within these arms orbit the galactic center at different speeds depending on their distance from the center, just as we discussed with rotation curves. This means stars should move through spiral arms rather than staying within them, and the arms themselves should wind up tighter and tighter with each galactic rotation, eventually becoming so tightly wound they disappear. But spiral arms persist, generation after generation, maintaining their open, graceful structure. The resolution to this paradox is that spiral arms aren't fixed groups of stars but rather density waves, regions where stars and gas temporarily concentrate as they orbit. Like cars bunching up in a traffic jam on a highway, stars slow down slightly as they enter a spiral arm, creating a persistent region of higher density even though individual stars pass through. But the mathematical details of these density waves remain puzzling. The integral curves, the paths that stars follow through the gravitational potential of a spiral galaxy, should produce certain patterns in the spiral arms. Yet observations sometimes show structures that don't quite match theoretical predictions. There are spurs and feathers extending from the main arms, branches that break off and reconnect in ways that simple density wave theory struggles to explain. Perhaps magnetic fields play a larger role than we thought, or maybe the interplay between stars, gas, and dark matter creates more complex dynamics than our models capture. Each spiral galaxy has its own personality, its arms showing unique features and quirks. The Milky Way's arms are different from those of Andromeda, which differ from those of more distant spirals. Understanding these integral curves and the forces that shape them would help us understand galaxy evolution, star formation, and the interplay between visible and dark matter in shaping cosmic structure. At the very heart of our own galaxy lies another profound puzzle. The Milky Way center is a crowded, energetic place, filled with stars, gas clouds, and powerful magnetic fields all orbiting around the supermassive black hole we call Sagittarius A star. Among the many strange features, there are long, thin filaments that stretch perpendicular to the galactic plane, glowing faintly in radio wavelengths. These galactic center filaments are enormous structures, some extending over 100 light-years in length yet only a few light-years wide. They appear to be magnetic field lines made visible by electrons spiraling along them at nearly the speed of light. But how did they form? What creates these orderly, thread-like structures in such a chaotic environment? The magnetic fields near the galactic center should be tangled and twisted by the motion of gas and stars, yet these filaments show a remarkable degree of organization, many of them running parallel to each other. One possibility is that they trace the boundaries between regions of different magnetic field strength or direction, like the seams where different magnetic domains meet. Or perhaps they're created by some energetic process we don't fully understand, possibly connected to the activity of the central black hole or to shock waves from ancient supernova explosions. The electrons generating the radio emission must be constantly replenished because they lose energy quickly, radiating away their speed as they spiral along the magnetic field. This means something is actively accelerating particles to extreme energies right now, today, in the galactic center. These filaments might be particle accelerators on a cosmic scale, natural laboratories where physics happens under conditions we can barely reproduce on Earth. Understanding them requires piecing together observations from many different telescopes, each seeing a different aspect of the phenomenon, slowly building a picture of what's happening in that distant, extreme environment at the heart of our galaxy. Looking beyond our own galaxy to our nearest large neighbor, Andromeda, we find another puzzle written in the distribution of its smaller companion galaxies. Andromeda has dozens of dwarf satellite galaxies orbiting around it, as does the Milky Way. These satellites should be scattered randomly around their parent galaxy, orbiting in all different orientations, pulled in from various directions during the galaxy's formation. But observations show that many of Andromeda's dwarf satellites orbit in a thin plane, like planets around a star, all moving in roughly the same direction. This is not what simulations of galaxy formation predict. Dark matter-dominated simulations produce satellites scattered in all directions, not organized into neat planes. The Milky Way shows a similar pattern, with many of its satellites also orbiting in a preferred plane. This could be a coincidence, but finding the same unusual arrangement in both nearby large galaxies suggests something systematic might be happening. Perhaps these satellites formed together in the early universe, as part of a larger structure that later broke apart. Or maybe there's something about how satellites get captured by large galaxies that naturally produces planar arrangements, some dynamical process we haven't properly accounted for in our simulations. Another possibility is that our understanding of dark matter is wrong, that it behaves differently on galaxy scales than we think. If dark matter interacts with itself even weakly, or if gravity works slightly differently than general relativity predicts on these scales, it might affect how satellite galaxies distribute themselves. The ordered arrangement of Andromeda's dwarf satellites is a small detail in the grand scheme of the cosmos, but small details often point toward deeper truths. It reminds us that even in our immediate cosmic neighborhood, within the small group of galaxies we can study in detail, mysteries remain. Perhaps the most massive mystery in every large galaxy is the supermassive black hole that lurks at its center. Nearly every substantial galaxy we've examined contains one of these monsters, with masses millions or billions of times that of the Sun. Our own Sagittarius A star weighs about 4 million solar masses. The black hole at the center of the giant elliptical galaxy M87, famously imaged by the Event Horizon Telescope, contains about 6.5 billion solar masses. These objects seem to be a standard feature of galaxy architecture, intimately connected to how galaxies form and evolve. But here's the puzzle. We don't know how they got so big. Supermassive black holes appear to have existed when the universe was very young, less than 1 billion years after the Big Bang. We've detected quasars, the brilliant beacons powered by matter falling into supermassive black holes, at times when the universe was only 5 or 6% of its current age. How did black holes accumulate so much mass so quickly? A black hole grows by consuming matter, but there are limits to how fast this can happen. As matter falls in, it heats up and radiates energy, creating pressure that pushes more matter away. This Eddington limit means a black hole can only roughly double its mass every few tens of millions of years. Starting from a stellar mass black hole formed from a dying star, it would take billions of years to grow to supermassive proportions, longer than the age of the universe when we see these early quasars. So supermassive black holes must have started from larger seeds, perhaps forming directly from collapsing gas clouds in the early universe, or from dense star clusters that collapsed into black holes. Or maybe the physics of the early universe allowed for different growth rates, with black holes feeding more rapidly than the Eddington limit would normally allow. Understanding how supermassive black hole seeds formed and grew is crucial for understanding galaxy evolution, because these black holes shape their host galaxies through their powerful gravitational influence and the energetic outflows they produce. At the heart of every black hole lies a boundary that has captured human imagination like few other concepts in physics: the event horizon. This is the point of no return, the surface beyond which nothing, not even light, can escape. For a distant observer, an object falling toward a black hole appears to slow down as it approaches the event horizon, its light redshifting and dimming, never quite seeming to cross that final boundary. Time itself appears to stop at the horizon when viewed from outside. But for the falling object itself, nothing special seems to happen at the event horizon. It crosses this invisible boundary in finite time, feeling no particular jolt or sensation as it passes. The event horizon is not a physical surface but a mathematical boundary in space-time, a one-way membrane in the geometry of space itself. What secrets does this boundary hold? According to classical general relativity, information about what falls into a black hole is lost forever, erased from the universe. But quantum mechanics suggests that information cannot be destroyed. This creates the black hole information paradox, a deep conflict between two of our most successful physical theories. Stephen Hawking showed that black holes should slowly evaporate through quantum effects, emitting radiation and eventually disappearing. But this Hawking radiation appears to carry no information about what fell in, seemingly violating quantum mechanics' fundamental principles. Some physicists propose that the event horizon is not as smooth and featureless as it appears, that it might be surrounded by a firewall of intense radiation that would destroy anything trying to cross. Others suggest that information is somehow encoded on the horizon's surface, written in subtle patterns that eventually get released as the black hole evaporates. The event horizon might be a hologram, a two-dimensional surface that encodes all the three-dimensional information about what fell in. These ideas push the boundaries of theoretical physics, trying to reconcile gravity and quantum mechanics in the most extreme environment imaginable. The information paradox represents one of the deepest problems in modern physics. When something falls into a black hole, it carries information: the positions and velocities of all its particles, the quantum states of all its fields. In quantum mechanics, this information never disappears. The universe maintains a complete record of everything, with past determining future through mathematical laws. But black holes seem to erase this record. Once something crosses the event horizon, no signal can emerge to tell us what went in. And when the black hole eventually evaporates through Hawking radiation, that radiation appears to be completely random, containing no information about what the black hole consumed. This suggests that information is destroyed, violating quantum mechanics. Yet both quantum mechanics and general relativity are extraordinarily successful theories, tested to exquisite precision. How can they both be right? Perhaps information isn't truly lost but is preserved in subtle correlations in the Hawking radiation that we don't yet know how to detect or decode. Maybe the evaporation process is more complex than we understand, with information emerging only in the final stages. Or possibly our understanding of spacetime itself is wrong. Some theories suggest spacetime is not fundamental but emerges from deeper quantum structures, and in these frameworks, black holes might not pose the same paradox. The recent idea of the ER equals EPR conjecture proposes that entanglement and spacetime geometry are deeply connected, that quantum entanglement literally creates the structure of space. In this view, information falling into a black hole might remain connected to the outside world through quantum entanglement, never truly isolated. Solving the information paradox will likely require a complete theory of quantum gravity, a framework that unifies general relativity and quantum mechanics into a single consistent description of nature. Until then, black holes guard this secret, their event horizons marking the boundary of our current understanding. Finally, we come to one of the most speculative ideas in cosmology: white holes. If black holes are regions where matter and light can only fall in, never escape, then the mathematics of general relativity suggests that white holes should also exist, regions where matter and light can only come out, never fall in. White holes would be the time-reversed version of black holes, cosmic fountains rather than cosmic drains. The equations of general relativity are time-symmetric, meaning if a black hole solution exists, a white hole solution should also exist. Yet we've never observed anything that looks like a white hole. This might be because white holes are fundamentally unstable. Even the tiniest amount of matter falling toward a white hole from outside would turn it into a black hole. Or perhaps white holes existed only in the very early universe and have long since disappeared. Some physicists have speculated that the Big Bang itself might have been a white hole, an eruption of matter and energy from something we cannot see behind the event horizon. Others wonder if white holes might exist on quantum scales, too small to observe directly but potentially playing a role in particle physics. There's even speculation that what appears to us as a black hole might actually be a black hole and white hole pair, connected through their centers, with matter falling into the black hole perhaps eventually emerging from a white hole somewhere else, or somewhere else. These ideas remain highly theoretical, mathematical curiosities that might have no correspondence to physical reality. Yet they remind us that our theories contain possibilities we haven't fully explored, solutions to equations that might describe aspects of the universe we haven't yet encountered. The cosmos might be stranger than we imagine, containing structures and phenomena that challenge our intuitions about how reality must work. White holes represent the kind of question that physics thrives on, ideas that push us to think more carefully about what our theories truly predict and what assumptions we make about the nature of time, causality, and the structure of spacetime itself. In the earliest moments of the universe, conditions were so extreme that matter and energy existed in forms we can barely comprehend. During the first second after the Big Bang, density fluctuations in the primordial plasma might have been large enough to collapse directly into black holes. These primordial black holes would be unlike the black holes we know from stellar collapse. They could have any mass, from less than an asteroid to thousands of times the mass of the Sun, depending on when and where they formed. Some might be microscopic, smaller than an atom yet containing the mass of a mountain. Others could be the seeds that eventually grew into the supermassive black holes we see in galactic centers. Primordial black holes have never been definitively detected, but they remain a tantalizing possibility because they could explain several cosmic mysteries at once. They might constitute some or all of the dark matter, the invisible substance that dominates the universe's mass. Unlike exotic particles that require new physics, primordial black holes are made of ordinary matter, just compressed beyond the point of no return. They would interact only through gravity, making them invisible except for their gravitational effects, exactly matching dark matter's observed properties. Astronomers search for them through gravitational lensing, looking for the telltale bending of light as a primordial black hole passes in front of a distant star. They also listen for gravitational waves from primordial black holes colliding and merging. Some of the black hole mergers detected by gravitational wave observatories might involve primordial black holes rather than those formed from dying stars. The mass ranges don't always match what we expect from stellar evolution, hinting that something else might be creating these objects. Yet proving they exist remains challenging. We need to rule out other explanations for the observations and find signatures that could only come from black holes formed in the universe's first moments. Until then, primordial black holes remain a ghost in the cosmic machine, potentially everywhere but not yet conclusively found anywhere. When black holes collide and merge, they send ripples through space-time itself, gravitational waves that we can now detect with exquisite sensitivity. These waves carry information about the masses and spins of the black holes, about how they spiral together in their final moments, and about the properties of the space-time around them. But some physicists have predicted that gravitational wave signals might contain subtle echoes, repeating patterns that would appear shortly after the main merger signal. These echoes would indicate that something unusual is happening near the black hole's event horizon. According to standard general relativity, the event horizon should be perfectly smooth and featureless, absorbing all waves without reflecting anything back. But if quantum effects modify the structure near the horizon, or if exotic matter exists there, or if the horizon isn't quite as absolute as we think, then gravitational waves could partially reflect off this modified region, bouncing back and forth between the horizon and the surrounding spacetime before escaping to our detectors. These echoes would be incredibly faint, buried in the noise of the detectors, requiring sophisticated analysis to extract. Some research groups have claimed to find hints of echoes in existing gravitational wave data, while others have disputed these claims, arguing that the signals could be statistical flukes or analysis artifacts. The debate continues as more gravitational wave events are detected and analyzed. If echoes are real, they would revolutionize our understanding of black holes, indicating that quantum gravity effects are measurable and that event horizons have more structure than classical physics predicts. They would provide our first observational window into the quantum nature of space-time itself. Among the billions of stars orbiting sedately in our galaxy, astronomers have discovered a small population of outliers moving at extraordinary speeds. These hypervelocity stars race through space at velocities exceeding the galaxy's escape velocity, moving so fast they will eventually leave the Milky Way entirely, sailing out into the void between galaxies. Some of these stars are moving at more than 1,000 kilometers per second, 10 times faster than the Sun's orbital speed. How did they get moving so fast? The most likely explanation involves the supermassive black hole at our galaxy's center. When a binary star system wanders too close to this monster, the black hole's gravity can tear the pair apart, capturing one star while flinging the other away at tremendous speed like a gravitational slingshot. This mechanism, called the Hill's mechanism after the astronomer who first proposed it, can accelerate stars to the extreme velocities we observe. But not all hypervelocity stars seem to come from the galactic center. Some seem to be moving too slowly, or their trajectories don't point back towards Sagittarius A star, suggesting other mechanisms might be at play. Perhaps gravitational interactions in dense star clusters can launch stars to high speeds, or maybe the explosion of a particularly massive supernova can provide the necessary kick. Understanding the true origin of all hypervelocity stars is essential for mapping the deep gravitational landscape of our galaxy, revealing not just the location and influence of the central black hole but also the dynamics of star clusters and the distribution of dark matter. These cosmic speedsters act as tracers, their trajectories providing clues about the invisible forces that shape our galaxy. Among the biggest unknowns in physics are the sterile neutrinos, hypothetical particles that might be crucial to understanding both dark matter and the universe's matter-antimatter asymmetry. We know of three types of neutrinos: electron, muon, and tau, all of which interact through the weak nuclear force and travel at nearly the speed of light. Sterile neutrinos, if they exist, would be far more antisocial, interacting only through gravity, hence the name sterile. This makes them a compelling candidate for dark matter. If sterile neutrinos have a mass in the kilo-electron-volt range, they could be the perfect warm dark matter, forming structures that are not too small, like cold dark matter suggests, nor too large, like hot dark matter suggests. They also offer a potential explanation for the universe's dominance of matter over antimatter. Neutrinos can change from one type to another, a process called oscillation, but for this to happen, neutrinos must have mass, which is a discovery that overturned the standard model of particle physics. The existence of sterile neutrinos could be linked to the masses of the ordinary neutrinos we observe, and their decay might have generated the matter-antimatter asymmetry in the early universe. Experiments are now searching for the faint X-rays that would be produced if a sterile neutrino were to decay into an ordinary neutrino and a photon, a signal that could finally reveal the nature of dark matter. So far, the evidence is tantalizing but not yet conclusive, leaving the sterile neutrino as a theoretical specter, a fundamental particle that could change our picture of the universe if it ever steps out of the shadows. All of these mysteries might find a surprising resolution if reality is fundamentally different from what it appears. The holographic principle suggests that our three-dimensional universe might be encoded on a two-dimensional surface, like a hologram that creates the illusion of depth. This radical idea emerged from studying black holes and trying to resolve the information paradox. Physicists realized that the maximum amount of information a region of space can contain is proportional to the area of its boundary, not its volume. This is strange because we normally think information scales with volume. A larger room can hold more books than a smaller one. But for fundamental physics, the boundary seems to matter more. This led to the proposal that everything happening in three-dimensional space might be fully described by information encoded on a two-dimensional surface surrounding that space. The universe might be like a hologram, where all the depth we perceive emerges from patterns on a distant boundary. In this view, gravity and space-time themselves are not fundamental but emerge from quantum information encoded on this boundary. String theory provides a concrete example of holography through the AD-SC-FT correspondence, a mathematical duality that equates a gravitational theory in a certain type of curved spacetime with a quantum field theory on its boundary. This has been proven mathematically for specific theoretical scenarios, though whether it applies to our actual universe remains uncertain. If holography is true, It would mean that the universe has fewer degrees of freedom than it appears, that the complexity we see emerges from simpler underlying structures. It would suggest that space-time is not fundamental but is constructed from something more basic, perhaps from patterns of quantum entanglement. The holographic principle might also solve various puzzles about quantum gravity and black holes, providing a framework where information is never truly lost but always encoded somewhere on the universe's boundary. Yet many questions remain. What is this boundary? Where is it? How does the encoding work? How does three-dimensional space with all its richness emerge from two-dimensional information? These questions push physics into territories where mathematics and philosophy merge, hinting that our everyday notions of space and time might be fundamentally misleading. Reality might be a projection, and the solid three-dimensional world we experience might be a kind of cosmic illusion, emerging from deeper structures that bear little resemblance to everyday experience. At the heart of quantum mechanics lies a phenomenon so strange that even its discoverers found it disturbing. Quantum entanglement creates connections between particles that seem to defy our ordinary understanding of space and separation. When two particles become entangled, measuring a property of one instantly determines the corresponding property of the other, no matter how far apart they are. You could separate entangled particles by the width of the galaxy, and still, when you measure one, the other immediately responds, not through any signal traveling between them, but through a connection that exists outside ordinary space. Einstein famously called this spooky action at a distance and believed it revealed some incompleteness in quantum mechanics. He thought hidden variables must exist, information carried by the particles themselves that predetermined their behavior, making the correlation only appear instantaneous. But experiments have shown that entanglement is real, that the correlation isn't due to hidden information but reflects something genuinely non-local about quantum reality. This entanglement is not just a curiosity, it might be the very fabric of space-time itself. The ER equals EPR conjecture, mentioned earlier in relation to black holes, suggests that the connection between entangled particles is the same thing as the wormholes or Einstein-Rosen bridges that connect distant regions of space-time. If true, entanglement literally creates the geometry of space, and space-time is merely a macroscopic manifestation of the intricate, non-local connections between quantum objects. This would mean that the deepest structure of reality is not a continuous, smooth manifold like space-time, but a network of quantum information, a web of entanglement where distances and closeness are defined by quantum correlation rather than by meter sticks. This profound insight, linking entanglement to geometry, is one of the most active and exciting areas of modern theoretical physics, offering a potential path to unifying gravity and quantum mechanics by showing that space-time emerges from quantum information. But it also raises fundamental questions. If space is created by entanglement, what happens when entanglement is destroyed or created? Does the geometry of space change? These are the kinds of questions that a fully unified theory of quantum gravity must answer. A more recent approach to understanding the quantum to classical transition is quantum Darwinism, which explains how classical reality emerges from quantum foundations through a kind of natural selection. In this framework, the environment constantly interacts with quantum systems, measuring them in effect, scattering photons and air molecules off objects, entangling with them in countless ways. Most of this environmental information is fragile and quickly scrambled, lost to the chaos of molecular collisions. But certain properties of quantum systems, certain pointer states, are stable under environmental interaction. These robust states proliferate their information throughout the environment, making many redundant copies. Position is a pointer state for macroscopic objects. The environment can easily determine where something is, and this information spreads widely. Other properties, like quantum phase, are fragile and don't survive environmental scrutiny. The environment acts as a selective filter, amplifying some information while destroying other information. We perceive classical reality because we're observers who interact with the environment, and the only information that survives to reach us is the robust, multiply-redundant information, the classical information that has been selected by the environment. We don't see superpositions or wave functions because the environment has already chosen one state and broadcast it everywhere. This elegantly resolves the measurement problem in quantum mechanics by showing that the act of measurement is not a mysterious collapse but an ordinary physical process of information transfer and selection. But what about the earliest moments of the universe, before complex environments existed? How did the initial classical structure emerge from the quantum foam? Quantum Darwinism provides a mechanism for the universe to choose a classical description for itself, a process that must have been fundamental in shaping the cosmos we see today. Of all the fundamental concepts that define our reality, perhaps none is more elusive than time itself. In our everyday experience, time flows inexorably forward, a river carrying us from past to future. But in the equations of physics, particularly general relativity, there is no such thing as a flow of time. The equations are largely time-symmetric, meaning they work just as well running backward as forward. The only physical law that specifies a direction for time is the second law of thermodynamics, which states that the total entropy or disorder of the universe must always increase. This increase defines the arrow of time, the distinction between past and future. But where did this arrow come from? If the universe started in a state of extremely low entropy, as the Big Bang suggests, then everything follows logically. But why did the universe begin in a state of such incredible order? This is the mystery of the past hypothesis, the assumption that the initial state of the universe had to be highly ordered for the second law to work and for time to have a direction. Some physicists and philosophers argue that time doesn't flow at all, that past, present, and future all exist equally in what's called the block universe. In this view, space-time is a four-dimensional structure where every moment exists eternally, laid out like frames in a film. The Big Bang and the end of the universe, your birth and your death, everything that ever was or will be exists simultaneously in the block. Time is just another dimension, like space, and moving through it is no different than moving through space, except that our consciousness only experiences one moment at a time. The block universe follows naturally from Einstein's relativity, which shows that simultaneity is relative, that different observers disagree about which events happen at the same time. If there's no universal now, no objective present moment that all observers share, then perhaps all moments are equally real, existing together in the eternal structure of space-time. This perspective dissolves the mystery of time's flow, replacing it with the puzzle of consciousness's experience. Why do we feel time passing? Is the feeling of a now an illusion created by our brains, or does the physics of the human brain somehow choose one frame of the block universe to perceive? These questions remain at the intersection of physics and neuroscience, pushing us to ask whether the subjective experience of time has a physical basis deeper than the purely objective laws of the universe. Even more exotic than the nature of time is the possibility of time travel. General relativity, the theory of gravity, permits solutions to its equations that involve closed time-like curves, paths through spacetime that bring an object back to its starting point in both space and time. These structures would essentially be time machines. One example is the traversable wormhole, a theoretical shortcut through spacetime that could link two different points in space and two different moments in time. Constructing a time machine would require exotic matter with negative mass or negative energy density, to prop open the throat of the wormhole and keep it stable. This exotic matter is not currently known to exist, though quantum mechanics allows for transient regions of negative energy. Even if a time machine could be built, the question of paradoxes looms large. The grandfather paradox, going back in time and preventing your own birth, has led many physicists to hypothesize that some fundamental principle must prevent time travel to the past. The chronology protection conjecture, proposed by Stephen Hawking, suggests that the laws of physics will conspire to prevent the formation of closed time-like curves, that any attempt to create a time machine will be thwarted by destructive quantum effects or uncontrollable feedback loops. No one has been able to prove this conjecture, and no one has been able to prove that stable time travel is possible either. Time travel remains a profound possibility lurking within the mathematics of general relativity, an unsolved problem that forces us to question the nature of causality itself. Even more exotic than time travel are tachyons, hypothetical particles that travel faster than light. In special relativity, particles with mass must move slower than light, while massless particles like photons travel exactly at light speed. But the mathematics allows for particles with imaginary mass, and such particles would be required to move faster than light, unable to slow down to light speed or below. These faster-than-light particles are called tachyons. If they exist, they would experience time differently than ordinary matter, moving backward in time from some reference frames. A tachyon moving forward in time in one frame would appear to move backward in another frame, creating potential for causality violations. Tachyons appear in some formulations of string theory as instabilities in the vacuum, signals that the theory is in an unstable state that will decay to something else. Most physicists believe tachyons don't exist as real particles because they would violate causality and create paradoxes. If tachyons could carry information, you could send messages to your own past, creating grandfather paradoxes. Yet searches for tachyons continue, looking for particles arriving before the light from the events that produce them, for anomalies in cosmic rays or particle accelerators that might hint at faster-than-light propagation. So far, nothing has been found. The universe seems to enforce the light speed limit strictly, preventing not just material objects but also information from traveling faster. This limit preserves causality, keeps the future from affecting the past in ways that would create contradictions. Tachyons remain whispers in the equations, mathematical possibilities that might be forbidden by principles deeper than the equations themselves, ghosts of faster-than-light particles that haunt theory but never manifest in nature. Among all the constants of nature, the fine structure constant stands out for its mystery. This dimensionless number, approximately 1/137, determines the strength of electromagnetic interactions. It governs how strongly electrons bind to nuclei, how light interacts with matter, the details of atomic spectra. The fine structure constant has no units, making it a pure number that appears in quantum electrodynamics as a fundamental parameter. Why does it have this particular value? No theory predicts it. We must measure it experimentally. If it were significantly different, chemistry would be dramatically altered. Atoms might not be stable, or might not form the variety of molecules needed for life. Stars might burn differently, altering the cosmic evolution that produced heavy elements. The fine structure constant appears finely tuned, falling in a narrow range that allows for a complex universe, stable stars, and the possibility of life. This fine-tuning is sometimes taken as evidence for the multiverse, that we only exist in a universe where the constant is in the right range, or as evidence for some deeper, underlying theory that fixes this value through some elegant mathematical principle. We also don't know if the constant is truly constant. Searches are underway to see if the value of the fine structure constant has changed over the billions of years of cosmic history, by observing the spectral lines of ancient light from distant quasars. Initial data showed tantalizing hints of a variation across the universe, suggesting the constant might change depending on direction or time, but subsequent, more precise measurements have mostly found it to be constant. The question remains, is the fine structure constant a fixed, arbitrary parameter of our universe, or a variable that points to new physics, perhaps a fifth force or a connection to extra dimensions? The very existence of such a precise, fundamental, but unexplained number sits at the heart of our attempts to create a unified theory of everything. The universe's seemingly fine-tuned constants and its tendency toward maximum entropy also give rise to a deeply strange philosophical puzzle, the problem of the Boltzmann brain. Given infinite time, even in a state of maximum disorder, heat death, random quantum fluctuations will eventually produce any possible structure, no matter how complex, given enough time. One such structure is a Boltzmann brain, a self-aware consciousness that spontaneously fluctuates into existence out of the cosmic void, complete with false memories of an entire lifetime and universe, only to quickly dissipate again. If the universe lasts for infinite time, then eventually the number of short-lived Boltzmann brains that fluctuate into existence will vastly outnumber the ordinary observers, like us, who emerged through billions of years of biological evolution. If we are typical observers, we should be a Boltzmann brain. But we perceive an orderly, low-entropy universe, not a chaotic, high-entropy void. This paradox, the Boltzmann brain problem, suggests that our current cosmological models, which predict a heat death leading to infinite time, might be fundamentally flawed or incomplete. Many of the proposed solutions involve modifying the initial conditions of the universe, modifying the laws of thermodynamics, or introducing a multiverse where the existence of observers is overwhelmingly dominated by those who evolved naturally in young, low-entropy regions. The problem forces us to ask, what is an observer? How do we distinguish a genuine, evolved consciousness from a random, short-lived fluctuation? It is a thought experiment that pushes on the nature of consciousness, time, and the boundaries of cosmological theory. Many of these puzzles, from fine-tuning to Boltzmann brains, have been addressed by proposing a multiverse, an ensemble of universes with different properties. Instead of one universe with mysteriously special parameters, there might be countless universes with all possible parameters. We naturally find ourselves in one where conditions allow our existence. In eternal inflation, bubble universes spawn endlessly, each with potentially different constants and laws. In the many worlds interpretation of quantum mechanics, reality branches into parallel worlds at every quantum event. String theory's landscape provides different vacuum states, each a possible universe. These multiverse ideas explain apparent fine-tuning without invoking design or fundamental principles that we haven't discovered. The parameters aren't special. We're just biased to observe them because universes with very different parameters don't produce observers. But the multiverse is controversial. Critics argue it's not testable, that if anything is possible somewhere in the multiverse, the theory can't be falsified. It might explain too much, becoming unfalsifiable because any observation can be accommodated by saying we're in the right universe for that observation. Defenders counter that multiverse predictions can be tested statistically, that we can ask whether our universe has typical properties among those that allow observers, and some multiverse theories make predictions about cosmological observables. The multiverse also raises philosophical questions about what makes a universe real. Do all these other universes actually exist, or are they just hypothetical possibilities? If they exist, do they have the same ontological status as our universe, equally real despite being forever beyond our observation? The concept of infinite branches, endless variations on existence, pushes at the boundaries of science and philosophy, suggesting that reality might be vastly larger and stranger than the observable universe, that our cosmos might be just one small patch in an infinite tapestry of possibilities. All of these cosmic mysteries, these questions about time and constants and multiverse, ultimately depend on the fundamental physics that operates at the extremes of density and temperature. The most extreme conditions in the observable universe exist inside neutron stars, objects so dense that a teaspoon of their matter would weigh billions of tons. Neutron stars form when massive stars collapse, crushing the core beyond the point where electrons and protons can remain separate, forcing them to merge into neutrons. The result is a ball of neutron-rich matter about 20 kilometers across, containing more mass than the Sun. At these densities, neutrons pack together as tightly as atomic nuclei, creating matter in states that can't be replicated in any laboratory. The physics inside neutron stars remains uncertain because we can't directly observe their interiors or recreate their conditions experimentally. The pressure at the core might exceed that found anywhere else in the universe except in black holes, reaching densities several times that of an atomic nucleus. What is the state of matter under such extreme compression? Is it just tightly packed neutrons? Or does the pressure squeeze the neutrons into more exotic forms, perhaps a superfluid of neutrons, a superconductor, or even a quark star, where the neutrons dissolve into their constituent quarks? The relationship between pressure and density, the equation of state for this ultra-dense matter, is one of the most important unresolved problems in nuclear physics and astrophysics. Measuring the properties of neutron stars, such as their mass and radius, particularly in binary systems where two neutron stars orbit and merge, provides data that helps constrain this equation of state. Gravitational wave signals from merging neutron stars, which we can now detect, are particularly valuable because they provide new windows into the physics of matter under the most extreme gravity and pressure. The quest to understand the neutron star interior is a search for the deepest secrets of matter, pushing our knowledge beyond what can be measured on Earth. Closer to home within our galaxy, globular clusters present another puzzle. These ancient spherical collections of stars, sometimes containing millions of stars in a compact region, orbit in the galactic halo, relics from the Milky Way's formation. Their stars are old, metal-poor, formed when the universe was young and heavy elements rare. Most globular clusters show mass distributions matching expectations, with stellar density highest at the center and declining smoothly outward. But some clusters have dark cores, centers where the stellar density seems lower than models predict. Telescopes looking toward these cluster centers see fewer stars than expected, as if something is missing or hidden. One possibility is that stellar mass black holes, remnants of dead stars, have sunk to the cluster center through dynamical friction, massive objects gradually settling to the middle as they exchange momentum with lighter stars. These black holes wouldn't emit light and would clear out the immediate vicinity of stars, creating a dark core. Another possibility is that an intermediate mass black hole, an object weighing hundreds or thousands of solar masses, resides at the core. Such black holes, too heavy to form from a single star collapse but too light to be a supermassive black hole, represent a missing link in black hole evolution, and globular clusters are the prime suspects for finding them. Or perhaps the core has undergone a core collapse, where the star density became so high that a runaway process occurred, eventually leading to a more diffuse core. The dark cores of globular clusters are a small but persistent anomaly in galaxy structure, a reminder that even the simplest stellar systems harbor complex, hidden physics. Finally, we turn our attention back to our own solar system, where a small, unassuming moon holds a dramatic secret. Mars has two small moons, Phobos and Deimos, irregular chunks of rock that orbit close to the planet. Phobos, the larger and closer of the two, has a peculiar fate awaiting it. Unlike most moons in the solar system, Phobos is gradually spiraling inward toward Mars, drawn closer by tidal forces that drain its orbital energy. Every century, Phobos drops about 2 meters closer to the planet, an imperceptible change on human timescales but significant over geological time. In roughly 50 million years, Phobos will cross within Mars's Roche limit, the distance at which tidal forces overcome the Moon's own gravity. At that point, Phobos will be torn apart, its material spreading into a ring around Mars, perhaps eventually falling to the surface as a rain of meteors over thousands or millions of years. This doomed orbit results from tidal interactions between Mars and Phobos. The Moon raises small tides on Mars, and the planet's rotation carries these tidal bulges ahead of Phobos's position, creating a gravitational pull that acts as a brake on the Moon's motion. As Phobos loses energy, it spirals inward, moving faster as it drops closer, eventually reaching its destruction. Phobos itself might be a captured asteroid, snared by Mars's gravity early in the solar system's history, or it could be debris from a giant impact, material blasted off Mars that coalesced into these small moons. Its interior structure remains uncertain, possibly a rubble pile, a collection of fragments loosely bound together rather than a solid rock. Understanding Phobos's composition and structure helps us predict exactly how it will break apart when it reaches the Roche limit, whether it will fragment gradually or catastrophically, and what kind of ring system it will create. Future missions might visit Phobos, perhaps even landing samples to Earth before this small moon meets its spectacular end. In the Jovian system, Io presents one of the most volcanically active worlds in the solar system, its surface constantly resurfaced by eruptions that coat it in sulfur compounds, giving it a yellow and orange mottled appearance. Io shouldn't be this active. It's a small moon, and small bodies cool quickly, losing their internal heat to space. Earth maintains geological activity through radioactive decay in its interior, but Io is too small for this to generate sufficient heat. Instead, Io's volcanism is driven by tidal heating. Jupiter's immense gravity raises tides in Io's interior, flexing the Moon as it orbits. Io's orbit is slightly elliptical, kept that way by gravitational resonances with Europa and Ganymede, so Io's distance from Jupiter varies as it orbits, and the strength of Jupiter's tidal pull changes accordingly. This flexing generates friction in Io's interior, heating it enough to melt rock and power hundreds of active volcanoes, turning Io into a furnace of internal stress. Even farther out, beyond Pluto's orbit, lies Eris, a dwarf planet similar in size to Pluto but more massive, orbiting in the scattered disk region of the Kuiper belt. Eris takes 558 years to complete one orbit, traveling as far as 14 billion kilometers from the Sun at its most distant point. At such distances, the Sun appears merely as a bright star, providing only feeble warmth. Eris's surface temperature hovers around 30 Kelvin, -243 Celsius, so cold that methane, which exists as gas on Earth, freezes solid into ice. Observations suggest Eris is covered in a bright coating, possibly fresh methane frost, giving it one of the highest albedos, highest reflectivities of any solar system object. This bright surface might indicate recent resurfacing, or it might be a mechanism of cryovolcanism, where gases and ices erupt onto the surface and then freeze. The most fascinating puzzle about Eris is its mass. Eris is about 27% more massive than Pluto, making it the most massive known dwarf planet. Its mass, combined with its high reflectivity and distance, makes it a critical object for understanding the outer solar system, forcing astronomers to rethink the boundary between minor planets and major planets. Eris is a world of extreme cold and distance, a testament to the immense, largely unexplored frontier that lies beyond the familiar planets, reminding us that the solar system contains secrets and objects that challenge our categories and expectations. Looking toward the far future, we confront questions about the universe's ultimate fate. The most likely scenario, based on current observations, is heat death, a quiet fade into maximum entropy. As the universe continues expanding, accelerated by dark energy, galaxies will drift apart, eventually moving beyond each other's cosmic horizons. Within each galaxy, stars will gradually exhaust their fuel. New stars will form for a while, but eventually the gas supplies will deplete. The last stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. Even these remnants will gradually fade. White dwarfs will cool, becoming black dwarfs, cold dark objects radiating no heat. Black holes will evaporate through Hawking radiation, slowly over timescales that dwarf the current age of the universe, but eventually even the largest black holes will disappear in a final burst of radiation. The universe will approach a state of maximum entropy, a uniform distribution of energy where nothing interesting can happen anymore, no stars shine, no planets orbit, no structures remain, just a cold, dark expanse with occasional photons and particles spread thinly across unimaginable distances. This heat death isn't a dramatic end but a gradual running down, like a clock slowly winding down until it stops. The timescale is almost incomprehensible, billions of trillions of years, but if current physics is correct, this is the ultimate fate awaiting the cosmos. Yet even in this far future, quantum fluctuations will continue, rare but inevitable, and given infinite time, every possible fluctuation will eventually occur, perhaps even fluctuations large enough to create new universes, new Big Bangs emerging from the quantum foam, beginning cycles anew. The heat death might not be the end but a transition to something we can barely imagine, a universe of pure potential waiting for the next unlikely fluctuation to crystallize into being. An alternative darker fate is the Big Rip, a scenario that might occur if dark energy behaves differently than we currently think. If dark energy doesn't remain constant but instead grows stronger over time, its influence will gradually become more dominant, overwhelming not just gravity between galaxies but eventually between stars, between planets, between molecules, and ultimately between atoms themselves. The expansion of space would accelerate without limit, creating a runaway process that tears everything apart. First, galaxy clusters would be pulled apart, then individual galaxies would dissolve as stars are separated. Planetary systems would break up, planets torn from their orbits and flung into the void. Eventually, even planets themselves would be ripped apart, their material pulled away atom by atom. In the final moments, atoms would be torn apart, electrons stripped from nuclei, and then nuclei themselves would be destroyed, protons and neutrons pulled apart into their constituent quarks. The Big Rip would be a final, total destruction of all structure in the universe, a violent end to everything, leaving behind only elementary particles receding from each other at infinite speed. The fate of the universe hangs on the precise nature of dark energy, its equation of state differing in details we haven't yet measured precisely enough to distinguish. Future observations will narrow these possibilities, telling us more about dark energy's properties and the universe's geometry. But perhaps some uncertainty will always remain, some ultimate mystery about what lies at the end of time. The universe's ultimate fate is in some sense our fate too, the backdrop against which all existence plays out, the final boundary of the cosmic story that began 13.8 billion years ago and will continue for timescales we can barely comprehend. In contemplating this far future, these vast stretches of time when stars will have long ceased to shine and matter itself might have decayed, we're confronted with our own temporariness, our brief flicker of awareness in a cosmos that extends so far beyond our brief moment. Yet we're also reminded of our remarkable position, existing at a time when the universe is rich with structure and possibility, when stars form and planets orbit and consciousness can emerge to wonder about it all, asking questions about beginnings and endings, about the nature of existence itself, questions that echo through the cosmos even as the universe, indifferent to our wonder, continues its patient march toward whatever ending awaits, whether that ending is billions of years away or trillions, whether it's quiet or violent, final or just another transition in an eternal cycle we can glimpse only through mathematics and imagination.